Hey everyone, and welcome. So have you ever felt completely stuck on the rate of reaction chapter in SPM Chemistry? Yeah, you're not alone, but you are in exactly the right place. Today, we're going to crack the code on this whole topic, and I'll show you how one single idea can make everything just click. Let's dive in. But first, real quick, understanding the theory is great, but practice is what really seals the deal for your exams. To really get this stuff down, you can head over to MCQSPM.com or just scan this QR code right here to get the app. It's seriously packed with questions to get you exam ready. So let's be real. Why does this topic seem so tough for so many students? I mean, you've got all these factors, right? Temperature, concentration, catalysts, surface area, and it feels like you have to memorize a completely different explanation for every single one. It's a lot. It's easy to get overwhelmed. But what if I told you that all of that, all those different factors, all those confusing graphs and questions, they all boil down to just one single powerful idea? If you can master this one concept, I promise you the entire chapter will make so much more sense. And that one idea, my friends, is the collision theory. Now, this isn't just another boring definition to memorize for the exam. Nope. Think of this as the master key. It's the key that unlocks every single question on the rate of reaction. So let's break it down.
Okay, so at its core, the theory is actually pretty simple. For chemicals to react, their particles have to literally bump into each other. They have to collide. But, and this is the absolute key, a super common mistake I see in exams, not just any old collision will do the trick. Only effective collisions actually lead to a reaction. So the whole game is figuring out how to increase the number or the frequency of these effective collisions.
So what's the secret recipe then? What makes one collision fizzle out and another one create a full-blown chemical reaction? Well, it turns out there are just two secret ingredients, two conditions that have to be met every single time.
Just think of it like a simple checklist. For any collision to count as effective, it has to tick both of these boxes. First up, do the particles have enough energy? We call this the activation energy. And second, are they facing the right way when they hit? This is what we call the correct orientation. Let's look at each one. Activation energy, which you'll see written as EA, is basically the entry fee for a reaction. It's the minimum energy needed to get things going. Imagine a horse trying to jump over a really high barrier. It doesn't matter how many times the horse runs up to the barrier. If it doesn't have enough energy to actually leap over it, it's never getting to the other side. Reactant particles are exactly the same. They have to clear that energy barrier.
And here is an awesome way to picture it. Think of the reactant particles as these little characters at the bottom of a huge mountain. To become products, they have to climb all the way to the top. That peak, that's the activation energy. Only the particles with enough kinetic energy to struggle all the way to the top can then enjoy the easy ride down the other side and become new products.
Okay, so what about that second condition? The absolute best way to think about it is like a key in a lock. Having the right shaped key, that's like having enough energy. But what happens if you try to put the key in the lock sideways or upside down? It's not going to work, right? You have to put it in with the correct orientation. And this slide shows that perfectly on a molecular level. Look on the left. The particles have enough energy, but they collide in a really awkward way. So what happens? They just bounce off each other. Nothing changes. But on the right, boom, they meet in that perfect alignment like a high five. Old bonds break, new bonds form, and you get a reaction. That is an effective collision.
Okay, great. We know we need enough energy, and we need the right orientation. So the next logical question is, how can we control this? How can we rig the game to make more of these effective collisions happen more often? Well, that's where all those factors that affect the rate of reaction finally come into play. These are basically the four big knobs we can turn to either speed up or slow down a reaction, and each one works by messing with our two key conditions. For today, let's just zoom in on two that are huge for exams: temperature and catalysts. So what's actually going on when we crank up the heat? Well, when you increase the temperature, you're giving all the particles more kinetic energy. They start zipping around like crazy. Now, because they're moving faster, yeah, they collide more often, but that's not the main reason the reaction speeds up. The crucial point is that way more of those particles now have enough energy to get over that activation energy barrier. So the number of effective collisions per second just shoots up, and so does the reaction rate.
All right, now for catalysts. Catalysts are super cool. A catalyst is basically a chemical shortcut. Just look at the diagram. Without a catalyst, our little particles have to climb that massive energy mountain on the left. But when you add a catalyst,
It's like a clever little helper comes along and builds a tunnel straight through the mountain. It provides a whole new, easier path with a much lower activation energy.
And listen up, because this is a major pro tip for your exams. This is something students mix up all the time. A catalyst does not give the particles more energy. That's what temperature does. All a catalyst does is lower the height of the mountain they need to climb. And with a lower mountain, way more particles already have enough energy to just cruise on over, which again increases the frequency of effective collisions.
Okay, enough theory. Let's get real and see how all this plays out in an actual SPM exam question. This is where the knowledge becomes power.
So here we have a classic diagram from a past paper. You can see two energy curves, labeled 1 and 2, showing two different ways the same reaction can happen. And the question asks, what change caused the reaction to go from the path with the high peak in curve I to the one with the much lower peak in curve 2? Just take a second and think. Based on what we just talked about, what lowers that energy peak? Let's walk through this using a super simple three-step strategy. Step 1. Just look at the diagram. What do you see? The peak of curve I is clearly lower than curve I. This means the activation energy went down. Simple. Step 2. Recall the theory. What's the only thing we talked about that actually lowers the activation energy? A catalyst. Step 3. Confirm your answer. Find the option that says a catalyst was added, which caused the activation energy to decrease. Done.
All right, so after all that, if you're going to remember just one thing from this entire explainer, what should it be?
It is this, right here. Every single question about reaction rate, I don't care what factor they give you, it all boils down to one thing, the frequency of effective collisions. That's it. Everything else, temperature, catalyst, concentration, it's all just a different tool to make more of these successful collisions happen every second.
So stop just memorizing lists of effects. Instead, really understand the two conditions for an effective collision, energy and orientation. Once you truly get how to play with those two keys, you can unlock any question the exam decides to throw at you. You've totally got this.
And just to leave you with a little something to chew on, we said a catalyst creates a new, easier pathway. But have you ever wondered what it is about the catalyst's own atoms and bonds that allows it to create this shortcut, all without getting used up itself? That's a little peek into the deeper magic of chemistry. Thanks for tuning in.